Let's start with a simple scenario. You send a request from one node to another on the network and wait for a response. The response doesn't come. What happened? Here is the critical insight. There are at least 6 completely different things that could have gone wrong, and from your position, sitting with no response, you cannot distinguish between any of them. 1. Your request was lost. Perhaps someone unplugged a network cable. 2. Your request is waiting in a queue and will be delivered later, perhaps the network or the recipient is overloaded. 3. The remote node failed. It crashed or was powered down. 4. The remote node temporarily stopped responding, perhaps it is experiencing a long garbage collection pause, but it will start responding again later. 5. The remote node processed your request, but the response was lost on the network, perhaps a network switch was misconfigured. 6. The remote node processed your request, but the response is delayed and will arrive later. Notice something important about this list. In cases 3, 4, and 5, the remote node may have actually executed your request. Your write may have happened. Your email may have been sent. Your money may have been transferred. But you have no confirmation. This is the heart of why distributed systems are fundamentally different. On a single computer, if a function call doesn't return, you know something is wrong with that function. In a distributed system, a missing response tells you almost nothing about what actually happened on the other side. The internet and most data center networks use asynchronous packet networks. One node can send a message to another, but the network gives no guarantees about when it will arrive, or whether it will arrive at all. And the only information you have when you don't get a response is exactly that: you haven't received a response yet. You might think, yes, these failure modes are theoretically possible, but surely in a well-managed data center they almost never happen. Let's look at the actual numbers. One study in a medium-sized data center found about 12 network faults per month. 12 per month. That's roughly 1 every 2.5 days. Of those 12 faults, half disconnected a single machine, and the other half disconnected an entire rack of machines. Not a bug in the software. Not a misconfigured application. The network itself, connecting machines in the same building, failed 12 times per month. Amazon EC2, the cloud infrastructure that powers a significant fraction of the internet, is notorious for having frequent transient network glitches. This is not a criticism, it is simply the reality of operating at cloud scale. The failures get stranger. Sharks have literally bitten undersea cables and damaged them. During a software upgrade for a network switch, network packets could be delayed for more than a minute while topology was being reconfigured. Every request during that minute would time out. And here is one that seems almost impossible: a network interface that sometimes drops all inbound packets but sends outbound packets successfully. The interface looks fine from the inside, sends data out fine, but receives nothing. Just because a network link works in one direction doesn't guarantee it works in the opposite direction. Another study found that adding redundant networking gear does not reduce faults as much as you would hope, because it doesn't guard against human error, such as misconfigured switches, which are a major cause of outages. Netflix built an entire tool called Chaos Monkey specifically to deliberately inject network failures into their production systems, because they recognized that if you don't test your code's behavior under network failures, you don't know what will happen when the inevitable real failure occurs. The lesson is not that networks are poorly engineered. The lesson is that even well-engineered networks fail, and your software must handle those failures gracefully. Many systems need to automatically detect faulty nodes. A load balancer needs to stop sending traffic to a dead node. In a database with single leader replication, if the leader fails, a follower needs to be promoted. How do you know when a node is dead? You might think the network can tell you. Sometimes it can give you hints. If the process crashed but the OS is still running, the OS will helpfully close or refuse TCP connections. You'll get a TCP RST or FIN packet in reply. HBase uses a script that notifies other nodes when a process crashes, so recovery can happen faster. If you have access to the management interface of the network switches, you can query them to detect link failures at the hardware level. If a router is sure the IP address is unreachable, it may reply with an ICMP destination unreachable packet. But all of these mechanisms are unreliable. TCP acknowledgement means the packet was delivered to the OS, not that the application processed it. The router doesn't have magic failure detection powers any more than you do. If you want to be sure a request was successful, you need a positive response from the application itself. And that brings us to the only truly reliable fault detection mechanism: timeouts. After some amount of time with no response, you give up and assume the node is not available. But here is the painful truth: there is no simple answer for how long your timeout should be. A long timeout means you wait a long time before detecting a fault, during which users see errors or delays. A short timeout detects faults faster but carries a high risk of incorrectly declaring a node dead when it has only suffered a temporary slowdown. And declaring a node dead prematurely has cascading consequences. Its load gets transferred to other nodes. Those nodes, now under higher load, may slow down. Other nodes may then declare them dead too. In the extreme case, all nodes declare each other dead and the whole system stops working. The cure becomes worse than the disease. Here is the phrase from the book that captures why there's no correct timeout value: asynchronous networks have unbounded delays. They try to deliver packets as quickly as possible, but there is no upper limit on how long a packet may take to arrive. And most server implementations cannot guarantee they will handle requests within some maximum time. Why are delays unbounded? It comes down to queuing. Think of traffic on a highway. Travel time varies most due to congestion. The same is true on a network. Consider the 4 layers of queuing a packet passes through. First, at the network switch, if several nodes simultaneously send packets to the same destination, the switch must queue them up and send them one by one. On a busy link, a packet may wait while others ahead of it are sent. If the switch queue fills up completely, the packet is dropped and must be retransmitted. Second, at the destination machine, if all CPU cores are busy, the OS queues the incoming network data until the application is ready to handle it. This wait can be arbitrary. Third, in virtualized environments, a running OS is often paused for tens of milliseconds while another virtual machine uses the CPU core. During that pause, incoming data just sits in the VM monitor's buffer. Fourth, TCP flow control, also called back pressure or congestion avoidance, where a node limits its own sending rate to avoid overloading the receiver, adding additional queuing at the sender. In public clouds and multi-tenant data centers, resources are shared. You have no visibility into what other customers are doing on the same physical hardware. A noisy neighbor running a batch MapReduce job can saturate the network link you share with them, making your timeouts fire even though your service is perfectly healthy. The conclusion the book reaches is important: variable delays in networks are not a law of nature. They are the result of a cost-benefit trade-off. A telephone circuit reserves guaranteed bandwidth for the duration of a call, bounded delay, but wasteful. The internet uses dynamic resource sharing, cheaper and better utilized, but unbounded delays. We chose the internet model, and now we live with the consequences. In the next section, we will find out that clocks are just as unreliable as networks.